All right, so we're going to discuss today Chapter 3, Part 2, which is about the logarithm. Definitely a related topic to the exponential. Hopefully you'll understand why by the end of this. So, logarithmic, Chapter 3, Part 2, and some definitions here. First of all, a logarithmic function with base b is a function of this type, f of x equals a times log base b of x. So that's a logarithmic function of base b. The logarithm itself, it acts like the opposite of an exponent, and hopefully I've got a visual that'll help you understand that more in a moment. But it asks the question, what power do I put on b to get x? What power do I put on the base to get the argument? So the base of the logarithm follows the same rules as the exponential. So the b has to be greater than 0 and not equal to 1. Same rules as yesterday. But there are some special bases. So every base that meets this criteria is valid. But there are some bases that are particularly useful. And the first is the common, which is base 10. And it's generally just written without the base. So if you see no base listed, it's understood to be 10. In the same way, if you don't see an index on a root, it's understood to be a square root. And no base on a logarithm means it's base 10. Why is 10 such an important number in our number system? It's the base of the system. Why do you think we chose 10? Is there something special about 10? Not all ancient number systems use it. Some ancient number systems, the Mayans, for example, use 20. The Babylonians used 12 and 60. Why do you think there's 60 minutes in an hour? Because the ancient Babylonian number system had a base 60, and they developed the time that we currently use. 10 is probably because we have 10 fingers, and every idiot can count to 10 as a consequence. And 20, that's when you pull out the old Kentucky calculator. Use your toes as well. But yeah, the natural world tends to use binary information. Your nervous system, for example. Your nerves can only send on or off to your brain, zeros and ones. So your brain takes that massive pile of zeros and ones and compiles it into the world we experience. So binary systems are more probably standard, but log base 10 is our common log. And then the natural logarithm is when we use Euler's number e as a base. And it's written in a really strange way. It's written as ln of x. And again, that's because in the Romance language, they put the adjectives after the noun. So instead of the natural log, it's the logarithm natural or whatever. It's developed by a French mathematician. Okay, any questions about what a logarithm is? Okay. Let's talk about why we would want to use it. So you've learned about exponentials and roots, and you've probably observed the relationship between those two things. So if I take something fairly obscure, let's say 2 to the 4th power equals 64. No, 2 to the 4th power equals 16, sorry. 2 to the 4th power equals 16. So I'll take this fairly unusual exponential relationship. I can write that as a root. Notice the output here is the 16 in this situation. So if I take the 4th root of 16, that's going to be equal to 2. I'll just show you in the calculator. So I've got these two, and you see how they use the same three values, but in this case, the output is the base. Here the output is the number that results when I raise this 2 to this power. Here the output is the base, but how could I get an output of the exponent? So there's three values here, and there are two outputs. Well, there's a third edge to this triangle, a third related operation, and it is the logarithm. So for this same relationship, I can say the log base 2 of 16 equals 4. So those are all ways to say the same thing. It's a way to yield the necessary exponent in an exponential relationship. And there will be some cognitive barriers here. So probably with the logarithm, for the first time, you'll really have to think about even the simple problems, because it's not intuitive for some reason, at least not at first. Wasn't for me. All right, so this is your book's explanation of what I just showed you. So let's evaluate some of these. Log base 2 of 16, well, we just talked about that one. That's 4. What power do I put on 2 to get 16? 4. There are ways to do these in your calculators, but for now, we're just going to work them out logically. So I had a calculus teacher tell me once long ago that you should remember the first 6 or 8 cubes and the first 4 or 5 fourth powers of numbers. You're going to be a high-level mathematician because they're so commonly used in problems. And I'll make that same suggestion to you guys because they don't use bases bigger than 4 or 5 or 6 in these problems because they'd be unwieldy otherwise, at least not commonly. All right, so log base 5 of 1 over 125. This one's a little tricky. So this asks the question, 5 to what power equals 1 over 125? Well, a couple things you need to know. You should know that 5 to the third power is 125. And you should also know that 5 to the negative n is 1 over 5 to the n. So use these two pieces of information, Holden, and tell me what the answer should be here. Very good. -3. Okay, moving on to the next one. Example 1, part C. Log base 3 of 1 over 27. Once again, asks us 3 to what power equals 1 over 27. So let's see here. Riley, what do you think about this one?
Negative.
Negative is correct. And what value? 3. Good, same as the last one. Which is kind of boring.
Yeah, that's fine.
It's kind of not great problem design. Not a lot of creativity getting thrown around here, but here's one that's going to make you think. So, Rachel, what power do I put on 17 to get 17? Very good. Just 1. Perfectly valid. Now, there are some rules for the argument of a logarithm. We haven't discussed these yet. But the argument of a logarithm, in other words, this part, whatever's inside the logarithm argument, not the base, has to be greater than 0. So we can't have 0 or negatives as the argument of a logarithm. So the argument must always be greater than 0. So here's one for you. Find for me log base 4 of 1 over 16. So weird to see Pat's class with like 4 kids in there. He usually has like 35 in his classes. Everybody wants him for art. Oh. Okay, so Bristol, what do you think here? Or to what power equals 1 over 16? Negative. Very good. All right. So basic properties of logarithms. These tell us some interesting things. You remember that everything to the 0 power is 1? So the log of any base when the argument of 1 has to equal 0. Doesn't matter what the base is. If the argument's 1, then you have to have taken it to the 0th power. So this is related to the notion that everything to the 0 power is 1. And then this is one that Rachel figured out. Log base b of b always equals 1. And the inverse properties of the logarithm and the exponential. So these are a little less obvious, but they're very important. So the log base b of b to the x power equals x. So in other words, you see there's an exponential in here in the argument, and the logarithm undoes it and gives you the identity function. And then for b to the log base b of x also just equals x. So the inverse relationship between the exponential and the logarithm is what makes the logarithm such a useful tool for us mathematically. Because for the first time ever, we'll be able to solve equations that have an exponent variable using the logarithm.
And where's the last one? XD?
B to the log base b of x equals x. Can get a little unwieldy if you let it. All this is in your book, but it is very important to know. All right, so let's evaluate one. So we have to know, and remember, I told you guys, knowing some higher powers of the first few numbers is important. So if I have 8, we know 8 squared is 64. And then 8 to the 3rd power is 512. So I'll make note of that over here. 8 to the 3rd power equals 512. So this asks us this question. And we see that that answer is, of course, just 30. So I could equivalently write this as log base 8 of 8 to the 3rd power. That's how they want you to apply those properties we just learned. Questions about that? Okay. To part B. Now this is formatted weird. All right, so I'm going to say this problem, Jesse, and you try to give me the answer. So this is 22 to the power I put on 22 to get 15.2. So what do you think, Jesse? So this is 22 raised to the power that if I put it on 22, the result is 15.2. All right, you can do it.
That's probably for this question. It's breaking in.
It's all right. I told you there's a cognitive barrier that must be overcome for these problems. It won't be intuitive in the way other math problems have been. So we're raising 22 to a power. If I were to use as the exponent on 22, the result is 15.2. Let me give you a hint.
Yeah.
Correct, but I'm hoping that you understand why. Because this is 22 to the power I put on 22 to get 15.2. We don't know what this number is, but we know as an exponent of 22, it yields 15.2. I know it's less than 1. Has to be a fraction, right? Because 22 to the first power is 22. So to get less than that amount, it has to be a decimal. But anyway, this property allows us to know that it is indeed 15.2. So it'll be easier the second time. Tell me what this one is, Ronnie.
4.
Very good. Yeah, the first time it's hard. After that, you'll see the pattern. Human brains are just spectacular at observing patterns. They're better than any computer on the planet at doing that. They're so good, they see patterns where none exist. Hence our mythologies and crazy stories historically. You know, we see patterns that we think the thunder is some great man in the sky throwing bolts of lightning. People try to explain things in the context that they understand. We see faces on Mars. I think it's called pareidolia. Anyway, some characteristic of the human brain where we see faces. You ever see a face in a cloud or maybe in a dark room in a closet? Faces where none existed is an example of your brain trying to make patterns out of nothing. So these are the same properties we discussed except for the common log. So they don't need to be noted a second time, but know that they apply to the common log as well. So when no base is listed, we understand the base to be 10. So the question here is 10 to what power is 10,000? Well, you just count the zeros. 1, 2, 3, 4. And the advantage here is this one is on your calculator, so those more exotic bases are not, but the common log is on your calculator, so we can check ourselves. Questions about that? Sorry, Rachel.
I just thought I had to write it down, sorry.
Oh, that's okay. I couldn't hear you.
Oh, sorry.
I'm terrible at hearing people with masks on.
You just said you counted the zeros in that height.
Mm-hmm. Because this is a perfect power of 10. If it were not, then I would have had to use the calculator. I could have given you a pretty good estimate, but without the calculator, you won't be able to evaluate non-perfect powers of the base. Okay, so it's a tricky one, Holden. This is 10 to the power I put on 10 to get 12. Very good. As I had hoped, it becomes instinctual after the first or second one. Stop me if you get confused.
I think.
Well,
Me too.
general levels of confusion are somewhat expected. If there's a specific question, be sure to ask it. But this is the power I put on 10 to get 12. And remember, if there's no base listed, it's understood to be 10. So I could also write this like so. So this little expression here, this means the power I put on 10 to get 12. And we're using that as the exponent of 10. So of course the result is 12. Log of 14. Well, now we got a problem. That is not a perfect power of 10. What power do I put on 10 to get 14? There's no exact answer here, so I'm going to have to use the calculator to approximate. And so what I do is log of 14. It's going to be 1 point something, 1.15 to the nearest hundred. And what's this? If I do 10 to the 1 point, and I'll use several decimals here so it'll be close. That's almost exactly 14. And the reason why it's not exactly 14 is I didn't use more decimals. Okay, so any question about how this works? All right, the logarithm. So remember my rules for the input of the logarithm? You see how we have a negative as our argument here? This is an invalid argument. And you don't try to evaluate it. We just say no solution immediately. We may never have a negative as the argument of a logarithm. And there will be problems from now on where you encounter this situation. You are to stop immediately and write no solution. I can't tell you how many times, going through this chapter, I've seen kids try to work these problems out, and they're doing an exhaustive amount of work trying to figure them out when it's just a no solution situation. Your calculator can tell you exactly that. If I try to say the log of negative 11, it's going to tell me to get lost. Okay, so log of 0.092. So the output of a logarithm may be negative. That's perfectly fine. And in this case, we're going to find that it is negative. So the log, there we go, of 0.092 is negative 1.04. When you approximate around, you should always use the approximately equal to symbol. You're sophisticated little mathematicians now, so you should use that practice. Set through so much math over the years. All right, so the natural log is also a case where all those rules apply that we discussed earlier. So just change that general base value b to e, and it all still holds true. Holds true for any good base. All right, so they throw a tricky one at us right away. Let's see if you can figure this one out. Holden. So the natural log of e to the 4.6 power. Very good. So, and I was going to rewrite that if Holden didn't get it right away as the log base e of e to the 4.6 power, and then it probably would have been a little more obvious. What's up, Ian? You just come in when you feel like it, I guess. All right. Let's see. No. All right, so talking about the logarithm. And the natural log, ln, that's base e. And the question the logarithm poses is, what power do I put on the base to get the argument? So the base is e. The argument is e to the 4.6 power. So the power put on e to get e to the 4.6 power is 4.6. That's the question at hand here. Part B, natural log of negative 1.2. What's this one, Bristol? Incorrect. Now remember our rules for inputs. This is less than or equal to 0, so it's invalid. Indeed. So be careful, don't just assume they will all decay in the way the simple ones we've studied so far have. You need to parse this information. Think about those rules we discussed. Okay, any questions? All right. Moving on. Part C. E to the natural log of 4. What do you think this one is, Rachel?
It's 4.
That's correct. And another way, I would have rewritten it like this if you couldn't figure it out. And that might have made it more obvious. So this is the power I put on e to get 4. That's what natural log of 4 means. So e to the power I put on e to get 4 is 4. It's like a little logic puzzle. If you're a computer scientist like Jesse, you probably get this pretty quick. Used to logic tests in computer science. If this, then that. You good, Rachel?
I think so.
Okay. Anybody else? Stop me if you got a question. All right. So D, natural log of 7. So this one is not going to evaluate easily. This asks us what power we put on e to get 7. Well, e is a non-repeating, non-terminating decimal. It goes on and on forever like pi. It's clearly not going to have 7 as a perfect power of itself. So we're going to have some exotic decimal value here. Probably 2 point something. So natural log is also on your calculator. And it's about 1.95 to the nearest 100. 1.95. You must engage with these logarithms to learn them. This is not something you'll get by accident. And if you don't study these carefully, the test will tell on you. It's going to be the easiest test for some, the chapter 3 test. The hardest for others. Because you're going to get a couple of these and like, wow, you missed that. You didn't pay attention. So, what do you think this one is, Roddy?
5.2.
Very good. All right, example 5. So let's talk about y equals log base 2 of x. I don't like that busy screen. So if we pick some x's and y's, I should never pick negatives or 0 for my x's because they are outside of the domain. Remember that the argument for the logarithm must be positive. So I must pick positive values. So I need to pick some positive values that are perfect powers of 2. If I don't pick perfect powers of 2, it won't be easy to construct this table. So I'll pick 1/4, 1/2, 1, 2, and 4. You guys see why I picked those values? You remember yesterday with the exponential tables, how those would be the y's? So the logarithm and the exponential are functional inverses of each other. So the x's become the y's and the y's become the x's. So I picked these values specifically because of their relationship to 2. 1/4 is 2 to the negative 2 power. 1/2 is 2 to the negative 1 power. 1 is 2 to the 0th power. 2 is 2 to the 1st power. 4 is 2 squared. So what power do I put on 2 to get these values? Well, that would be these values. And so now I've constructed a little table. So first point, positive 1/4, negative 2. Next point, positive 1/2, negative 1. Next point, 1, 0. Next point, 2, 1. And then 4, 2. So we see this distinctive logarithmic growth shape. Now, I want you to consider for a moment, you remember we did y equals 2 to the x. Do you see how those are inverses of each other? If I were to dot in y equals x, each is the reflection of the other in that line. So log base 2 of x, let's talk about its characteristics. First of all, the domain. It's going to be x greater than 0. You remember how the range for the exponential was y greater than 0? Well, here we have its inverse has that same range for its domain. So the domain is x greater than 0. The range is going to be y is a real number. In other words, any y is valid. Let's see what else they wanted here.
Wait, can you go back to that?
Yes, I will. Intercepts, asymptotes, in behavior. So in this case, only the x-intercept is defined, and it's at x equals 1. So the asymptotes, it has a vertical asymptote at x equals 0. See that here. And then in behavior. So the limit as x goes to infinity of f of x is infinity. And the limit as x goes to negative infinity of f of x does not exist. It is outside of the domain. And then intervals of behavior. There's only one interval from 0 to infinity, and it is always increasing. So there's a graphical analysis of y equals log base 2 of x. There's a trick to put these in your calculator, but I'm not going to show you just yet. I want you to try these problems from homework using just this technique.
What if we say already know how to do it?
Yeah, well, then that's beyond my control, sir. As Einstein famously said, the teacher can only ever give a student the opportunity to learn. Ultimately, the onus or the burden of the task is on you. I'm here only to point the way. Like the Mandalorian. This is the way.
is coming out soon.
Next month.
Yeah.
I'm super excited.
I'm
Yeah, that's the best Star Wars IP in a long time, bro.
definitely.
Maybe ever. Because I'm as excited watching that as I was, Return of the Jedi and when I was a little kid. Okay, so let's do log base 1/3 of x. So this is kind of weird because we have to choose powers of 1/3, but that's really just powers of 3 because 1/3 is 3 to the -1. So let's choose 1/27, 1/9, 1/3, 1, 3, and 9. So 1/27 is 1/3 to the 3rd power. 1/9 is 1/3 squared. 1/3 is 1/3 to the 1st power. Not in this case. See how it's a fraction to begin with?
Oh,
So that's a good question, Jesse, but let me show you why. So the negative powers in this case are actually going to come in down here.
oh my gosh.
So 1/3 to the 0 power is 1, and then 1/3 to the -1 power is 3, and 1/3 to the -2 power is 9. So as Jesse pointed out, this can be a little bit counterintuitive when you start out with a fractional base, because they're sort of the opposite of the previous situation. This is logarithmic decay. The last one was logarithmic growth. Need 9 units there. Didn't quite make my line long enough to fix that. One, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So 1/27, in other words, right next to the y-axis, goes up to 3. Use a different color. And then 1/9 goes to 2. And then 1/3 goes to 1. And 1 goes to 0. And 3 goes to -1. And 9 goes to -2. So here we have, hard to draw that way, logarithmic decay. Sure. He had that hint of panic in his voice that makes me immediately say, okay. So, all right, domain is going to be x greater than 0. The range is going to be y is a real number. The intercepts, there's only an x-intercept, and it's at x equals 1. And then there's asymptote. There's a vertical asymptote at x equals 0 in behavior. So that's going to be the limit as x goes to infinity of f of x, which is -infinity, and the limit as x goes to -infinity of f of x, which does not exist. Let's see, what else am I missing here? Intervals of behavior, I guess. And so the interval of behavior, only one, 0 to infinity, and it will forever be decreasing mystery. Stop me if something confuses you here, guys, while I investigate our home invasion. He's grabbing the hot patch. That's okay, bud. No problem. So domain, range, intercepts, asymptotes, end behavior, intervals of behavior. The same thing we've been doing with graphs all through this book. Very graphical book, very visual book. Interpretation and analyzation of graphs are a big part of what we do. And that will continue to be the case. All right. 100. Anybody need more time?
What was the outline down there at the bottom? Yeah,
Does not exist. So negative infinity is outside of the domain of this function, and so the limit doesn't make any sense. And this is a mathematical way to say it doesn't make any sense. Just write D and E, does not exist. Okay, so not a great question. Okay, so here we go. Logarithmic growth and logarithmic decay. So if you have a base greater than 1, you're going to have this logarithmic growth pattern. If you have a base between 0 and 1, like our second example, you'll have this logarithmic decay pattern. And these characteristics will hold for all of the family of logarithmic functions, no matter what the base is. If it meets this criteria and it isn't modified or transformed in some way, these characteristics will hold true. So let's do a transformation. So we're talking about log of x versus log of x plus 1. This is example 6, I believe. Yep. So the plus 1 here is going to do what sort of transformation, Ian? Left 1 unit. Very good. So if I were to graph the log of x it's going to have some pretty funky characteristics. It's going to be a lot steeper than the ones we've done so far. So first of all, I would have to pick values that were perfect powers of 10. So I have 1 over 10 would go to negative 1, 1 would go to 0, and 10 would go to 1. So that would be, and then way out here somewhere, be like that. So the graph would look something like this. So if I slide that 1 unit to the left, just take these points. Not quite that much steeper. Something like this. Let's graph it on our calculator and see how we did. So log is easy to graph on the calculator because it's a built-in function. Log of x, and then log of x plus 1. Graph. Yeah, see how poorly your calculator handles asymptotes, or at least this one does? Let's change our window so we get at least a little bit better view. This will focus right around where the action happens. Yeah, this actually goes down, down, down to negative infinity, even though it appears to stop. And so frequently, guys, so frequently, when I have a quiz question about graphing a logarithm, somebody gives me this right here. In other words, they don't take it on down and put the arrow because they only know what the calculator tells them. So this is not a perfect graph. This will not get full credit. You need to indicate to me that it goes down, down, down to negative infinity. All right. So we have log of x and then negative log of x minus 2. So Jesse, there are two transformations taking place here. Tell me what this one's going to do.
Then I'll flip it over to you.
Very good. What's this one going to do, Rachel?
That one is, isn't that your y?
Well, remember when we have something added or subtracted to the input for a function, that's going to shift us right or left. And it goes to the opposite of the way you'd expect. To the right, how many units? Good. So I'll just do a more quick sketch here. And we're going to flip this over the x and go right to. So it's going to be something like that. Let's see how the calculator feels about it. This is just right here in the, actually we need more. We need to go at least to 5 or we won't be able to see what's going on. All right. Everybody see how that works? Transformations of a logarithm. Need a bunch more of those. So logarithmic scales are important because you can have a much greater range. Logarithms are used to measure things that have huge variability, like earthquakes, for example. So the intensity of an earthquake is logarithmic in the terms of the Richter scale. And so for every number, that's an additional power of 10. So a 7 on the Richter scale is 1/10 as strong as an 8 on the Richter scale. Now both of those would be catastrophic earthquakes. But you see how a 1 or a 2 would be so infinitesimal by comparison? Barely feel it. We recently had an earthquake here that my wife said woke her up. I didn't even notice it. She's particularly sensitive to such things. Once in 2013, it's a long, long time ago, I was teaching an Algebra 1 class. It might have been 2012. Anyway, somewhere around there. Teaching an Algebra 1 class, and I noticed the screen just almost imperceptibly jiggling like this. And I thought, wow, that's weird. So then I continued the problem. Later on, I read we had an earthquake. So that was the result. So that's a really tiny earthquake. You know, Tennessee isn't subject to the big ones. But out in California, you know, they live on a fault line that is probably the most dangerous one on the planet, the San Andreas Fault. And eventually it's going to break and California will fall into the ocean. Probably not for a very long time, but eventually it will happen. Much to the chagrin of Democrats, because California is the primary reason why the Democrats win so many electoral votes. Okay, so let's talk about this situation. So here we have this formula, and I'm going to see. I wonder if I can move this around because that's almost illegible the way it is. Yeah. There we go. So the Richter scale measures the intensity, which is the R of an earthquake, and it uses a formula where the amplitude in microns of the vertical ground motion, that's how far up and down the ground moves. T is the period of the seismic wave, so how long the wave takes to repeat itself as it radiates out from the epicenter. And B is the factor that accounts for the weakening of the seismic waves. So if you're so far away, how much weaker is it compared to the action going on at the epicenter? Find the intensity of an earthquake with an amplitude of 250, a period of 2.1, and B equals 5.4. So this is the reason why I'm going over this one. I usually skip some of these problems, but the reason why I do this one is there's a test question about it, and it's pretty often missed. So R equals log, and remember A is our amplitude. So our amplitude is 250. And then they tell us T is the period, which is 2.1. And then B is the weakening of the seismic waves. And in this case, that's a factor of 5.4. So I just plug this in the old calculator. Just have to figure out what goes where. It's about 7.48. So that would be a catastrophic earthquake if that happened in real life. Hey.
Sorry.
It's okay, no problem. All right, any questions about anything we have discussed? Hopefully you're now well acquainted with the logarithm, and you'll have the last 15 minutes or so to work on the following. Page 178, 2, 8, 12, 14, 25, and 28. If you get stuck on one, be sure to ask me about it.